If you've not taken a look at the lecture video on 1.2 that comes in a WebAssign with the book, then I would encourage you to watch through that video before you watch this. But this is an example of some of the even problems listed for homework in the homework assignment 1.2. Section 1.1 goes over some differences between pre-calculus and calculus, some applications where we could solve them with pre-calculus in the past, but we couldn't solve similar applications with pre-calculus. For example, if we have a triangle, we can get the area of that shape using a formula. But if we have an area defined by some function, for example, this, and we want to get the area underneath that curve on an interval, that's not a standard geometric formula. So how do we get that area? And there are lots of other situations that we would come across where we would use calculus that we couldn't do in pre-calculus. I'll mention one more. If you have a straight line, or even a curved line, a curve, if you have 2 points, if you pick any 2 points on a straight line or on a curve, you can get the slope between those points. Of course, if it's a straight line, then you have the same slope throughout. So we could calculate the rise over run between those points and get the slope. Now, if it's a curve, we have different slopes at different locations, but we could draw a line between those 2 points and get the rise over run. That's referred to as a secant line, and we could find the slope there. What we could not do in the past is if we had a curve, find the slope at a single point. Now, we could estimate it by drawing a line that appears to be tangent, but keep in mind that the way we calculate slope is rise over run, or the difference in y's over the differences in x's. But if we only have 1 point, how do we do that? We can't get a difference in the y's if we only have 1 y, and we can't get a difference in x if we only have 1 x. So how do we go about doing that? So these are some issues that we will run across in calculus. So we're going to start building up some tools in order to figure out how to solve some of these problems. But I would encourage you to go back, watch the video on section 1 as well in WebAssign, just to get kind of an idea of why are we doing calculus? Why are the things that we've done in pre-calculus not sufficient enough? They're solvable problems that we may have never thought about that we couldn't do in the past, but we can develop a way to do those using calculus. So this chapter is dealing with limits, and let's go through solving this problem. If we were to directly substitute a 0 into this function, sine times, or 7 times sine over x, we would get 7 times sine of 0 over 0. And remember, we can't divide by 0. That's undefined. In this case, though, let's see what happens to the top. Sine at 0 is 0. 7 times 0 is 0. So this is undefined because we have 0 on bottom, but this was referred to as being indeterminate. Indeterminate. And in the lecture video, it should discuss the difference between normal things that are undefined in cases where we are indeterminate. So we're undefined here when x is 0, but let's pick some values around 0 and see what our function does. Let's start over here. If we look at a number line and we want to know what is our function doing at 0, if we plug that in and it's undefined, we can pick a point to one side of it and put in. So if we put a 0.1 in and we do 7 times sine of 0.1, and that needs, your calculator needs to be in radians. So sine of 0.1 divided by 0.1, we get 6.988. 6.988. So while we don't know exactly what's happening other than being undefined at 0, if we scoot over just a little bit, we get this value for our function. Well, let's get a little bit closer. Instead of being a tenth to the right, let's be a hundredth to the right. So if we put in 0.01, we could do 7 times sine of 0.01 divided by 0.01. And let's go to 4 decimals here. This would be 6.9999. So while the 6.88, that was close to 7, this is even closer to 7. Now let's get really close to 0. Let's put this in. So if we put a 0.001 in, we have 7 times sine of 0.001 divided by 0.001. And that's 6 let's see, 1, 2, 3, 4, 5 nines. The next one would round up, so 6 and 6 nines. Now the instructions in WebAssign will let you know how many decimal places to round to. But notice as our x value gets closer and closer to 0, our answer is getting closer and closer to 7. It gets closer and closer to 7. So that's what a limit is. If our x value, our input, approaches a particular value, what does our output get closer and closer to? So at least coming from the right side, our y value appears to be getting closer to 7. But we need to check from the other side. So if we go a tenth to the left and put in a negative 0.1, take sine of negative 0.1 and divide by negative 0.1, we get 6.988. If we put in negative 0.01, we would end up getting 6.9999, and then we would get this here. So as we let our x's on the left side of 0, here's 0, if we let our x's get closer and then closer to 0, notice if I plug that number into my function, that's not 0, but that's closer to 0 than that is. So if we let our x's get closer and closer to an x value of 0, what is our function doing? Well, it's getting closer and closer to a y value of 7. So we say that the limit as x approaches 0 of the function 7 times sine x over x is 7. Or you could read it, the limit of this function as x approaches 0 is 7. So as our x's get close to 0, what do our y's get close to? Alright, so here's a visual. They tell us to use this graph. So this is the graph of the function 4 minus x, 4 minus x. And here's x equals 1, x equals 2, x equals 3, x equals 4. They tell us find the limit of that function as the x value gets close. So here is an x value of 3. So if we were to start out, let's do this. If we were to start when x is 0, we would be up here at 4. But if we let x get closer to 3, now we're at a y value of 3. If we let x get closer to 3, now we're at a y value of 2. Now we're at a y value of 1. So I'm starting over here, and then I'm letting my point get closer and closer to this x value. And I want to know in the y direction, in this direction, what y value am I getting closer to? So as this slides down closer and closer to this x value, I'm getting closer and closer to that y value, which is 1. So the limit of this function, when x gets close to 3, that y value is getting close to 1. So when x is almost at 3, y is almost at 1. Now in this case, the limit and the function are the same value. If we substitute a 3 into this function, we get an answer. And if we were to make a table like we did in the previous problem, if we picked points a little bit to the right of 3, our y values would be getting closer and closer to 1. If we picked points a little bit to the left of 3, our y values would be getting closer and closer to there, which is a y value of 1. So what are we getting closer and closer to? We're getting closer and closer to a y value of 1. One thing that's going to be important to note is we have to be approaching the same y value from both sides. As we slide down the graph, getting closer and closer to, let's do this. Here's an x value of 3. As we slide down the graph and we get closer and closer to that x value of 3, we're also getting closer and closer to this y value of 1. And that occurs from both sides. If we follow this line and we let it get closer and closer to the yellow line, we're also getting closer and closer to y equals 1. All right, let's go on to the next one. Now let's look at this one. Here, where are we taking the limit? We're taking the limit as x approaches -5. Now let's compare that with taking the limit as x approaches 4 of that same function. So this graph is a graph of this function. We don't have to make a table to see what our limit is here. So if we want to see what happens when x is close to 4, not necessarily 4, but close to 4, let's look at points where the x value is close to 4. So when the x value is here, my answer is 1. When the x value is here, my answer is 1 and 1. If I go over here, when I put this x in, the answer is 1. At this x, the answer is 1. So as I'm getting closer and closer to an x value of 4, the y value here is 1. The y value there is 1. And that's true on both sides. Now why did I do that? Because I want to contrast that with what happens when x is -5. If we start to the left of -5, if we put this x value into our function, our y value would be -1. If we put this x value into our function, our y value would be -1. And as long as we're getting really, really close to an x value of -5, our y values are going to be down at -1. So from this side, we're approaching this point right here, which has a y value of -1. Now, if I pick a point to the right of -5, like -2, if I put a -2 into this function, my y value comes out to be +1. If you don't believe me, put a -2 into this function and simplify. But since this is the graph of that function, this is what the y value would be, +1. If I pick a -4 for x, when x is -4, y is 1. And as close as I get to -5, when I put points really close to -5 in, I get a y value of 1. Now, if I were to put -5 in directly, on bottom I would have -5 plus 5, which is 0, and I'll have the absolute value of 0 on top. Now, that doesn't reduce to 1. If we have a 0 on bottom, it is undefined. So this is indeterminate. It doesn't reduce to 1. So notice what happened. When we picked points to the left of -5, our y value approached -1. When we picked points to the right of -5, our y value approached +1. If we are approaching different y values from each side of our input, then this limit does not exist. So D and E, that limit does not exist. For the limit to exist, we have to be going to the same value on each side like we did here. When we followed down and got close to an x value of 3, and when we started over here and got close to an x value of 3, both of those were directing us to that point, which corresponds to 1. But here, if we pick points on one side, we're going towards this point. On this side, we're going towards this point. So as x gets close to -5, what are we going to? Well, we don't really know for sure. That limit does not exist. Here's another example of a limit that does not exist. And let's look at y. If we were directly substitute a 0 in, we would have 1 over 0 inside the cosine. Well, this is undefined. How do you take cosine of something that is undefined? Well, that's going to be undefined, or perhaps indeterminate. We don't really know what that means. How do you take cosine of an undefined quantity? Well, let's think about what would happen. Let's just make a quick little table. If x is getting closer and closer and closer to 0, this quantity is actually getting closer and closer to either positive or negative infinity. Let's compare letting the denominator get smaller and smaller, and let that denominator get closer and closer to 0. Well, this one is 1, this one is 10, 100, 1,000. Well, what happens when we take cosine of values that are getting increasingly large? Is that going to be going to anything in particular? And the answer to that is no. If we look at a cosine wave, the cosine wave does this. It goes back and forth, back and forth. It has a maximum of 1, a minimum of -1, but it constantly oscillates. So for various x's, sometimes we're going to get an answer for which cosine of that value is 1, not in this case. Sometimes we're going to get cosine of something that has a value of -1. Again, not necessarily those exact cases. But as our x gets closer and closer to 0, our input is getting bigger and bigger and bigger, or the inside of cosine is getting bigger and bigger and bigger, which doesn't drive us to anything. It just oscillates back and forth between positive 1 and negative 1, positive 1 and negative 1, positive 1 and negative 1. So pick numbers close to 0, and then closer to 0, and then closer to 0. We're not narrowing down. We're just oscillating back and forth, back and forth, back and forth. When we get to 0, we're actually undefined, so there's not actually a point there when x is 0. But everything around it, we're back and forth, back and forth, back and forth. So in that case, we're not approaching a specific outcome. We're between two outcomes, but we're not approaching a particular one, so that limit does not exist. Now here they give us this graph, and they ask us some questions, and I've got the answers shown, but let's see why those answers are what they are. So the first question is, what is f of 1? So remember, in this notation, if this is our function f, this is the x value, and we're looking for what y value corresponds to the x. So here is an x value of 1. So where is our point when x is 1? Well, our point is here. So when x is 1, the corresponding y value is 2. So f of 1 is 2. When x is 1, y is 2. So then the next part asks us, what is the limit as x approaches 1? So let's approach 1. Let's start to the right side of 1. So we're starting here. If we let this point get closer and closer to an x value of 1, then we're approaching that point, which has a y value of 1. But let's pick a point on the other side of 1. Let's pick a point over here. This has an x value of 0. So we got close to 1. We got close to 1 starting over here. We got close to 1. Now let's start over here. And let's get close to an x value of 1 and see what happens. Well, if we let this point get closer and closer and closer to an x value of 1, here the x value is almost 1. That x value is about right here. So that x value is almost 1. That goes up here. Looks like a y value of about 5. So if on one side our function goes towards one y value, and on the other side our function goes to a different y value, same x here, we're ignoring what actually happens when we get to 1. But when we're close to 1 on the left and when we're close to 1 on the right, our functions are going to two different locations, so that limit doesn't exist. So then what is f of 5? So there in the function is the x value. So here is where x is 5. Is there a point that has an x value of 5? And the answer to that is no. If we look right there, there's something missing. When x is 5, there is no point. Hence, that does not exist. There is no point in existence when x is 5. So what about the limit at 5? If you can see this, what about the limit to this function as x approaches 5? So let's describe it this way. Let's take this line, let's thicken it up a little bit. So if we didn't already know, then we don't know exactly what is happening when x is 5 because it's hidden. So let's look around 5. Let's look around an x value of 5. So if I start over here, and I let my x value get closer and closer to 5, then it's following my curve up to here. So it's following it that way. And that looks like we're getting closer and closer to an x value or a y value of 2. Now let's start over here. If we put a point over here into our function, our answer is up here. And then as we let our x value get closer to 5, then our answer is going to be getting lower and lower and lower and lower until we get closer and closer to this point. Now, we don't know what's happening behind there. We don't know what's behind the curtain, but it appears from looking around it that from the left side and from the right side, we're approaching a y value of 2. So that limit that approaches 2. Now you may remember what happens behind there. What happens behind there is that there's a hole. Is there a point where x is 5 and y is 2? And the answer to that is no. But that's not what a limit is. A limit is what is happening around the x value in consideration. So if we're near this x value, then what y value are we close to? So that things around an x value of 5 give us answers that are close to a y value of 2. Now, I know that can be confusing. The more times you do it, the more it makes sense. And you're like, okay, that's not so bad. The easiest way to make sense of this is to go back to a table. Make yourself a table and plug numbers in closer and closer to something and see what is my function doing. We'll do that with one more example. Let's look at the example x squared minus 4 over x minus 2. If we directly substitute the point 2 in, we get 2 squared, which is 4 minus 4, and 2 minus 2. So we get 0 over 0, which that's undefined, but that's indeterminate. So the question remains, well, what is our limit? If we can't just plug a number in and get an answer to this, what is happening around an x value of 2? So if 2 is here, let's go a little bit to the right of 2, let's say 2.1. And if we put a 2.1 into our function, we have to be careful how we do this, but 2.1 squared minus 4, that's the top. And if we do 2.1 minus 2, we would get 0.1 on bottom, so we get negative 3.9. If I type that in correctly. And I don't think I did. I think I had something left in my calculator. So let's try that again. So we had 2.1 squared minus 4. So we have that divided by 0.1. So yeah, so that should be 4.1. So when we put this x in, we got this y. Now let's get a little bit closer to 2. Let's get within 100th of 2. So if we put 2.01 into our function, we square it, subtract 4, and that gives us the top. And then divide by 2.01 minus 2, which is 0.01, and that gives us 4.01. So we're letting our x value, this is close to 2, it's 0.1 to the right, a tenth to the right. This is closer to 2, this is 100th to the right. If we get even closer to 2, if we get 1,000th to the right, we would get 2.001 squared minus 4 divided by 0.001, and that's 4.001. So notice as our x value, not when it reaches 2, because when we reach 2, we're undefined, we're indeterminate. But when our x value gets closer to 2, our y value is getting closer and closer to a y value of 4. If we go to the left of 2, 1/10, if we go to the left 1/10, then we would be at 1.9. So if we put in 1.9 and divide that, 1.9 minus 2 would be negative 0.1, so we would get 3.9. That's 1/10 away. If we get closer, if we get 100th away, we would be at 1.99, and this turns out to be 3.99. If we get 1,000th away, we would be at 1.999, and this would turn out to be this. So here our x is smaller than 2, but it's getting closer to 2 and closer to 2, not quite to 2, but getting really close. And our answer is getting closer and closer to 4. So while at 2, we're indeterminate, if we let x get close to 2, not all the way to 2, but close to 2, the things around it, the neighbors around it, appear to be getting closer and closer to 4. So this is what we're approaching. So this is our limit.